So let's get started. Today we are going to continue our discussion regarding the equilibrium of particle. So last time we talked about the equilibrium of a particle, and we mentioned that when a particle is in equilibrium, it means that the particle it's at rest, and I can say that the summation of the forces acting upon that particle is going to equal 0. And also we talked about the free body diagram, and we know the importance of the free body diagram in order to apply the equations of equilibrium. It means that I need to draw the free body diagram. It's going to assist us in order to apply the formula. Also, we talked about the coplanar force system. In the coplanar force system, the forces acting in XY plane. And we said that in order to solve a problem like that, we are going to dissolve the forces into X and into Y components, and then we are going to apply the equation of equilibrium. Today, we are going to talk about the last thing in that chapter, which is equilibrium of a particle. We are going to talk about how we are going to deal with three-dimensional force systems. Last time we talked about two-dimensional force system, the coplanar. This time we are going to talk about three-dimensional force systems. So, like I said last time, we talk about 2D particle equilibrium. Here I have a particle which is in equilibrium, but the system here is coplanar. All the forces lies in XY plane. Of course, we need to draw the free body diagram, show all the forces acting on the particle. I need to dissolve the forces into their rectangular components. Then I'm going to apply that formula, which is going to be in a form of summation of the forces in X direction is going to equal 0, and the summation of the forces in Y direction is going to equal 0. And then I'm going to have two unknowns and two equations. I can easily solve that. If I'm going to have more than 3 unknowns, then it's impossible to use the equation of the equilibrium alone in order to solve the problem. So the maximum numbers for unknowns in 2D system is going to be 2. If I'm going to have more than 2 unknowns, then the equation of equilibrium is not enough in order to solve the problem. Today, we are going to look at the 3D particle equilibrium. We are going to deal with a particle within equilibrium in 3D dimension. We are going to deal with X, Y, and Z. And also, we know that the summation of the force vectors is going to equal 0. But this time, when we are going to break down that formula here into their magnitudes components, we are going to have 3 formulas. The summation of the forces in X axis here is going to equal 0. And the summation of the forces in Y axis here also is going to equal 0. And the summation of the forces in Z direction also is going to equal 0. So in 2D, we used to have 2 equations, but in 3D, we are going to have 3 equations. So the maximum number for unknowns here in that system is going to be 3 unknowns. If I'm going to have more than 3 unknowns, then it's not possible to get a solution using the those equations alone. So today we are going to talk about the how to solve a problem involve particle equilibrium in 3D. And the steps are going to be the same as 2D, except that we are going to have additional equation here, which is the summation of the forces in z direction is going to equal 0. Also, that equations, it could be expressed in Cartesian form. We're going to say that the summation of the forces in x-axis I plus the summation of the forces in y-axis j plus the summation of the forces in z-axis k is going to equal 0. Of course, if that's the case, that means I'm going to equate the summation of the forces of I here. I'm going to equate it to 0, and also I can equate that summation to 0, and also I can equate that summation to 0. So here I have a system of 3D. We have a particle which is in equilibrium, but this time it's in 3D. So like I said, that the procedure is going to be the same. Here, first, if I'm having the problem here, I'm going to draw the free body diagram. And in order to do that, we know that the first thing need to be done is to draw the x, y, z axis. So first I need to establish x, y, z axis. This is the first step need to be done regarding the free body diagram. Then I'm going to label known and unknown forces. I'm going to include the magnitude and the direction, like here. And if I don't have the direction of the unknown forces, I'm going to assume the direction. So if you don't know the value of the unknown, you need to assume the direction. And then if I'm going to do that, then I will be able to use the equation of equilibrium. Then, like last time, before using the equation of equilibrium, I need to decompose the forces into their components in x, y, and z components. Then I will be able to use these three equations. Sometimes it's not easy to decompose the forces into their components. So if that's the case, then the problem is going to be complicated. And in order to solve it, I need to express all the forces here as Cartesian form. If you do remember, when we were dealt with Cartesian form, we say that using Cartesian form is convenient, especially when we are dealing with three-dimensional problems. So if the problem is complicated and you cannot resolve the forces into their components, in that case, you need to express all the forces here into their Cartesian form. So if the problem looks difficult, express the forces in Cartesian vector form, and then we are going to use the general equation, which is summation of the forces of the vector is going to equal 0. Then set I, j, and k components to 0. And we are going to solve two problems today. We are going to have example 1 and example 2. In example 1, we are going to resolve the forces into x, y direction because it's easy. In example 2, we are going to express the forces into their Cartesian form, and then we are going to set I, j, k components to 0. So let's get started here. We are going to start with example 1. Like you can see here, I have a system of cables in order to hold a load equals 90 pounds here using that hook. So here I have a load of 90 pounds, and here I have knot A, and it's connected with 3 cables. I have AD and I have AC, and I have AB. And the cable AB, here we have spring. And we know that when we have spring, when force is applied, we are going to have change in length. So it's also required to calculate the stretch here in AB, because we have spring. And of course, the constant of the spring is given here, equal 500 pound per foot. And the question here, they want to determine the force in the cables. So I need to know FD, F from AD here from that cable, and FC here, FAC. And also I need to know the force AB, and then I need to know the stretch in AB. Here he gave us a note. He said that the cable AD, this cable here, lies in XY plane. And that's it's very important point here, because I'm not going to resolve the force, or I don't have any component in X in Z direction. That means easily I can resolve the force AD into X and into Y. And also he said that the cable AC lies in X and Z plane. Also, it means that I don't have any component in Y axis. So also that is going to facilitate the problem. The problem is going to be simplified, because I'm going to decompose the force only in X and into Z here, regarding the force in cable AC. So that's the problem. So now we need to solve the problem here. Like you said, like we said before, the first step need to be done. We need to draw the free body diagram. In order to do that, I'm going to draw the free body diagram for the node A. So I'm going to isolate the node A from the surrounding, and then I'm going to see the forces acting on that node here. So first I have the weight of the box, which is down. So here I have W, which equals 90 pound. Then I have the force here, FAB, or you can say that FD. And here we have the force from the cable AC. We can call it FC. And here we have the force AD. We are going to call it AD. So here we have that knot. We have the force down, W. We have the force from the spring here, FB. We have the force from the cable here, FC. And we have the force from the cable here, FD. And the force here lies only in XY plane, and the force FC lies only in the plane ZX. So now we need to solve the problem. We draw the free body diagram. We need to apply the equation of equilibrium. This time, how many equations do we have? So this time we are going to have 3 equations. We have the summation of Fx equals 0, summation of Fy equals 0, and summation of the force in Z direction equal 0. I'm going to draw the X, Y, Z axis. Then I'm going to, in order to apply those equations, I need to resolve the forces into X, Y, Z components. So let's start with FD. Since FD lies only in XY plane, I can easily resolve the forces into X and into Y. So I'm going to start with FD. I'm going to have component in X and component in Y. The component in X is going to equal the magnitude FD multiplied by sine 30. The other one in Y direction, I have component here in Y is going to equal FD times cosine 30. So this one is going to be minus, while this one is going to be positive. Then now I finish from that force. I successfully resolve it into x and y. Then I'm going to take the Fc, since the force here is only lies into xz plane. Then I have the proportional triangle. We'll learn how to deal with this. So I'm going to have components into x. It's going to equal Fc times 4/5. And then I have a component into z equals Fc times 3/5. So now I successfully decompose Fc into x and into z. This one is going to be negative, and this one is going to be positive. Then I have Fb. So regarding Fb, since the Fb is already located into y-axis, then I don't need to do anything with it. I will put it as it is. And also for the weight W, since the W is directed along the Z direction, also I'm going to put it as it is. So now I successfully resolved all the forces into X, into Y, and into Z axis. Now I'm in position in order to use the equations of equilibrium. So I'm going to start with summation of forces in x direction equal 0. Here we have the x-axis. I'm going to put all the forces in the x-axis. I'm going to equate it to 0. So here I have that force here, which is Fd sine 30, and it's positive. Here I have Fc times 4/5, which is negative. So I have only two forces. I'm going to add them together with their signs. It's very important, and equate them to 0. So here I have Fd sine 30, which is positive. I have minus Fc times 4/5, which is negative. The summation should equal 0 since the particle is in equilibrium. Then I'm going to move to the second equation, which is the summation of the forces in y-axis should equal 0. Here I have also two forces. I have that force and I have that force. The force here is positive and the force here is negative. So I'm going to have Fb here, which is positive, and I have Fd cosine 30, which is negative. I'm going to add them together with their signs. We call this algebraic summation of the forces, and we are going to equate them to 0. Then I'm going to use the third equation, which is the summation of the forces in z direction equal 0. Here I have that force and that force. The force here is going to be positive since it's up, and that force here is going to be negative since it's down. Then if I apply this equation, I'm going to have this force here, Fc times 3/5 positive, and here the weight is negative, minus 90 pounds equals 0. Now I have three equations and I have three unknown forces. I have Fd, which I don't know. I have Fc, which I don't know also. And I have Fb, which I don't know. So I need to solve that system mathematically. I have three equations, three unknown. I can't solve them using the math. It has nothing to do with static. At the end of the lecture, I'm going to remind you how to solve three equations with three unknowns using the calculator. Okay, so let me give you like a small tutorial how to solve the equations using the calculator, because we need to save times. We need to save time here. So if you are going to solve this system here, we are going to find that FC is going to equal 150 pound, FD equals 240 pound, FB equals 207.8 pound. Now we answer the first part from the problems, which is the forces into the cables. Now we know the forces in the cable FB and FC and FD. Also, it's required in that example to calculate the stretch in FD. Here we have spring. So when I apply that force, I'm going to have a stretch. And we are going to say that FB here is going to equal the spring constant here for that spring multiply times the stretch. So we managed to calculate all the forces in the cables, but we want to calculate the stretch. So we know that the relation between the force and the spring, the force acting on that spring, which is FB, equals the constant of that spring times the stretch in AB. We calculated the FB, and the K is given. So FB is 207.8 pound, and the constant here is 500 pound per foot, which is given. Then I have this value and that value. Easily I can calculate the stretch, and the stretch here came out to be 0.416 foot. And we managed successfully to solve the problem here. So do you have any questions regarding that example? Please, I give you the chance now in order to ask question about the problem here. Okay, since you don't have any questions, then I'm going to move to example 2. So now we have example 2. In example 2, we have a system here in order to carry a box that weigh about 100 kilogram. So we have a system here. It's made from 3 cables in order to carry that box here, and the weight of that box is 100 kilogram. We need to determine the tension in each cord or cable. We need to know the tension here in AC and AB and AD. And also, since we have a spring here, we need to calculate the stretch in AB. So the stretch in AB is required as well. And it's easily if I know the tension in AB, like the previous example. Like any problem like this, the first step is to draw the free body diagram. So I'm going to draw the free body diagram for that problem. I'm going to draw the knot A and isolate it from the surrounding in order to know the forces acting on that knot here. So if I isolate the surrounding from the knot A, I'm going to see that I have a force which is acting down because due to the weight of that box. And I'm going to have a tension here in the cable AB, tension in AC, and tension in AD. So the free body diagram is going to look like that. I have weight down, and I have FD, and I have FB, and I have FC. So like you can see here, the force here is not laying or lying in the certain plane. So this one, it has component into X and into Y and into Z axis. The same goes for AC. We have components into X and Y and in Z. And AB here, it's simple. It has only one component into X, and the weight here, it's easy. It has only one component into Z. So if I have problem like this one here, remember I mentioned that if the problem looks difficult like this one, we are going to use different strategy this time. So here you are going to express all the cables, the forces in the cables into Cartesian form. So this time the strategy is totally different. We are going to express all the forces here into their Cartesian form. So I have the problem. I draw the free body diagram. I want to use the equation of equilibrium, which is those equations. This time, it's difficult to use them because in order to use them, I need to decompose the forces into their components. And since it's like you can see, it's difficult to decompose this one into X, Y, and Z, and this one also into X, Y, and Z, I'm going to I'm going to express them into Cartesian form vector. So please pay attention here that point is very important. So in order to express a force into their Cartesian form, we remember that if I have F vector is going to equal Fxi plus Fyj plus Fzk. So I need to convert all the forces here into that form. So let's start with FB. FB here is easy. I'm going to say that the vector FB here, of course, this one here is expressed in the bold form, or if you wanna to express it into italic form, you need to put an arrow here to say that this one here is a vector. So the FB vector equals FB. FB here is magnitude followed by the letter I. And I should write plus 0K, 0J plus 0K. But since I don't have components into Y and Z, I don't need to write those parts. So since I have only one component in X-axis, I'm going to say that the FB vector equals FB magnitude followed by the letter I only. You could write plus 0J plus 0K to show that I don't have any components into Y-axis and Z-axis. Similarly, I'm going to express the vector W here in Cartesian form. And if you haven't noticed, regarding the W vector here, I have only one component into Z. Then what should I do about it? As you might have guessed it, we are going to say that W vector is going to equal the magnitude 981 followed by which letter? Is it I? No, I don't have components in I. Is it J? I don't have component in J. So the force is directed only along BZ. So this one is going to be only followed by the letter K. And also it's very important to notice this, the direction is negative. So I'm going to say that the W vector equal the magnitude, which is negative, followed by the letter K. So that was easy to express the FD and the W vector. Now I have C and I have D. Regarding the C, he already gave us the alpha and beta and gamma. And we know that F vector is going to equal the magnitude followed by the letter I plus the letter plus the magnitude by the letter J plus the magnitude by the letter K. And we know that the magnitude, it could be expressed into cosine alpha and cosine beta and cosine gamma. We have other form for that. And in order to do this, we are going to say that the FC is going to equal FC cosine alpha, which is here. So this one here represent the component into X. And regarding the component into Y, I'm going to say that FC cosine beta, which is 135 degree. And the component into Z is going to be FC cosine 30 K. So using the direction, I'm able to express the FC vector. Now, like you can notice, we are going to use all the information in the previous chapters in order to solve the problem here. Now, regarding the force in AD, he gave us the coordinates, the coordinate in X, Y, and Z. And we'll learn how to convert this one into a force vector. We are going to use the position vector, and then from the position vector, I'm going to convert it to unit vector by dividing by its magnitude, and then multiply by the magnitude of the force in order to have a force vector. So in order to solve or to express the force AD here into vector, I need to know the coordinates. And the coordinates here is -1 and 2 and 2. Then the position vector is going to be -1i plus 2j plus 2k. And I need to convert this one to unit vector. Unit vector is the position vector over its magnitude. So if this one here is the position vector, I can easily calculate the magnitude. So it's going to be this part squared plus that part squared plus that part squared. And then when I multiply by the magnitude of FD, we are going to have the FD vector. So if you simplify that formula, we are going to have the FD vector. Now, I managed to express all the unknowns into Cartesian form. Now, I'm gonna use that formula here. It's a general formula, which is summation of the forces vectors is going to equal 0. I'm going to calculate the resultant. So the resultant is going to equal the FB vector plus FC vector plus FD vector plus the W vector. And since the system is in equilibrium, we are going to set the equation to 0. FB represent FBI, FC represent minus 0.5 FCI, minus 0.7 or 7 FCJ, and plus 0.5 FC. Okay. Regarding FD represent those three terms here, and W represent that term here. Now, I'm going to set or equate the I components into 0. So here is the I component, and this one is I component, and this one is I component. I'm going to equate that component into 0. So I'm going to say that the summation of the forces in X is going to equal 0. I have FB, which is the component of I. I have minus 0.5 FZ, which is a component of I as well. And finally, I have minus 0.33 FD. I'm going to equate all of this into 0. Then I'm going to say that summation of fy is going to equal 0. I'm going to set the component of j into 0. I have this part and I have that part only. So minus this part plus that part is going to equal 0. Then finally, I'm going to equate the components of j of k to 0. I have that part, and I have that part, and I have that part. I'm going to equate them into 0. Now I managed to apply the 3 equations, but this time I convert all the forces into their Cartesian form in order to do that. Now I have 3 equations, equation 1, equation 2, and equation 3. And how many unknowns do I have here? I have FB, FC, and FD in all the 3 equations. So now I have a system of 3 equations and 3 unknowns. And if you are going to solve the problem simultaneously, you are going to find that FC is going to equal 830 Newton, FD is going to equal 862 Newton, and FB is going to equal 694 Newton. And now we successfully calculated the tension in the cables. Also, it's required to calculate the stretch in AB. And since I know the force in AB, which is FB here, and I know the constant of the spring, I know that the force acting on that spring is going to equal the spring constant times the stretch. So FB here equals the K, the constant here, times S. So the force here, I have 694, is going to equal 1,500. I convert this one into Newton per meter instead of kilonewton per meter, because the value here is Newton, so that to balance the units, balancing the units is very important. And I need to multiply this by 1,000, so it's going to be 1,500. Then if I solve for S, I'm going to find that the stretch in that spring is going to equal 0.462 meter. So in order for that system to carry that force here, we are going to have stretch in the chord AB about 0.462 meter. I'm going to stop here. If you have any questions regarding that problem. So basically I have 2 strategies, either to decompose the forces into X and Y, if it's that possible, like example number 1. And sometimes it's not easy to decompose the forces into their components. So in that case, I need to express the forces into their Cartesian form, and then I'm going to get the resultant, and then I'm going to equate the components of I to 0, and that represent the summation of fx equals 0. And I'm going to equate the components of j to 0, and that represent summation of the forces in Fy equals 0. And I'm going to equate the components of the k, and that represent the summation of Fz equals 0. Now I have a system of 3 equations and 3 unknowns. Okay, I'm going to stop here. If you have any questions regarding this, please be my guest.